Hi guys, welcome to the lesson of partial differential equation. So in this class, we are going to discuss the compatibility condition for a Neumann problem, and we will also solve an example to understand this problem. So here we are given with an equation that is the Laplace equation. We know that it is given by u double x plus u double y is equals to 0, right? So this is also called potential equation, and this is basically second order linear partial differential equation, and also called two-dimensional steady heat equation, and well known as Laplace equation, right? So the boundary conditions are given here. That are the Neumann boundary conditions. Derivative at boundaries are given. For this problem, this necessary compatibility condition should hold if it has a solution. Otherwise, we can say that this problem do not have a solution, right? So the condition is that the integral of gx dx minus f of x plus ky minus hy should be equals to 0 in the given intervals. So here is the idea for this compatibility condition. We have an equation, Laplace equation, that is actually u double x. It's a function of x comma y plus u double y. It is a function of x comma y, and that is equals to 0, right? So we can integrate this equation with respect to dx dy by applying the limits for x and y. So here we can see that the integral is from 0 to b and then 0 to a uxx dx dy. We basically split these two functions uxx and uyy. So we have the integral uxx dx dy and uyy dy dx. Now we can integrate this function. So first of all, for this function, we integrated this function with respect to x, so we get ux of x comma y, because we know that the integral of f double prime x is equals to f prime of x, right? So here it is ux x comma y, limits are from 0 to a, and for uy, limits are from 0 to b. We will apply the limits here. So upper limit then minus lower limit, and upper limit minus lower limit, that is equals to 0. So now we can plug in the values that are given in the boundary conditions. So uxa comma y is ky, ux0 comma y is hy, and then similarly this one. All right, so now we can write it independently with the integrals. So we have the form of the compatibility condition, and we can see that this is the condition which should hold for this Neumann problem for Laplace equation, right? So here we have a question that is a Laplace equation, and the boundary conditions are given. U0 comma y is g of y, ux a comma y is h of y, and then these are 0, right? So for this problem, if the boundary conditions are given in this way, we can split the problem into two parts. That is, we can compute the problem for one boundary condition and then for the second boundary condition. All right, non-homogeneous boundary conditions, actually. These are the non-homogeneous boundary conditions, right? So we will split the conditions here. We can see that u1 xx plus u1 yy is equals to 0. First of all, we will compute for g of y, and we will make this one 0, and these are already 0, right? And for we call it static, this equation. And for the second equation, that is u2xx plus u2yy is equals to 0, we call it hash. And boundary conditions will be like this. Now this is non-homogeneous and all other conditions are homogeneous, right? So if all the boundary conditions are given non-homogeneous, so we have to calculate in this way. U of x comma y will be equals to u1 plus u2 plus u3 plus u4, and we can compute individually, right? So it will be equals to u1 plus u2 plus u3 plus u4 in the case if all the four boundary conditions are non-homogeneous, right? So here's the formulation for the solution. First of all, we will solve this static equation. So we know that the solution for this equation will be given by these two functions. Now we'll apply the boundary conditions here. Y of 0 is 0, which implies c is equals to 0 from here, right? And then for y is well, y of b is equals to 0 implies that d sine pb is equals to 0. So we can get the eigen value from this equation, right? So the eigenvalue for the problem is p is equals to n pi over b. We will plug in the equations, and here we can see that we have applied the boundary condition for x, that is x prime of a is equals to 0. So from here we can see that we have this function a is equals to b to the power negative pa or e to the power pa. Now we can plug this back into the original equation, and here we can see that this is basically we replaced the value of we plugged the value of b here, that is b to the power negative pa over pa times px, and then here p to the power negative px. Now we multiply this function by e to the power pa and divided by e to the power pa to take this e to the power pa and e to the power pa common. So we will move it outside, and b is also common in both, so we will move it outside as well. Now we have e to the power px minus pa plus e to the power negative px plus pa. So for p, we know that it's equals to n pi over b, so we can replace here with n pi over b. Then we have n pi over b times x minus a, and here minus n pi over b times x minus a, right? We will divide it by 2 and multiply by 2 to make it a hyperbolic function. So here it is cos hyperbolic n pi b times x minus y. This will be converted into a hyperbolic function because we know that e to the power x plus e to the power negative x divided by 2 is equals to cosine hyperbolic x, right? So we have the angle here, that is instead of x, it's n pi over b times x minus a. So here we can see that this is the angle, right? So now we have the solution for x in this manner, and now we will multiply it by y, that is d sine n pi b over y, right? Here is the function. So the general solution, we can write it in the form, because 2b over 2b times d, we can write it as bn, and over e to the power n pi over b is again a constant, so we'll write it as it is, and then we have particularly the general solution here, right? So now we have to work for the particular solution, so we will apply the non-homogeneous boundary condition to compute this bn, and from here we can see that bn is equals to 2e to the power n pi over b over b cosine hyperbolic n pi over b, and limit 0 to b in this integral. This is the Fourier sine series, right? So for this bn we can plug here, and we will generate the particular solution for this static problem. So the static problem is solved. Now we will move on to the hash problem, and we have this problem here, right? u2xx plus u2yy, and the boundary conditions, this is now 0, this is kept non-homogeneous, these are already given 0. The solution is given by these two functions, right? We will apply the boundary conditions again here. X of 0 is equals to 0 implies c is equals to negative d. Therefore, x of x is equals to 2c sine hyperbolic n pi x over a, because here what we did, we simply plugged c is equals to negative d here, that is negative c. So we know that e to the power x plus e to the power negative x, sorry, not plus this time, it's minus this time, over 2 is equals to sine hyperbolic x, right? So we multiply and divide it. Here you can see this 2, It's because of that we divided here to make it a sine hyperbolic function, right? And now we can multiply both the functions, x times y, then again 2c times b is equals to an. So the general solution for this hash problem is given by this equation, right? So for the particular solution, now we need to compute the derivative because the non-homogeneous boundary condition is the derivative boundary condition. Derivative for this problem is here. Then we will compute this an, right, by simply keeping this an on the left hand side and shifting all these onto the right hand side. So this is a constant now, cos hyperbolic n pi a over b. I will make a rectangle here. This is constant, this is also constant, and this one we know that will make a Fourier sine series, right? So here you can see it's 2 over n pi over b times b cosine hyperbolic n pi a over b, and limits 0 to b with this function, right? So we will integrate this function to get the value of an. Then we will just plug this an back to the equation here, and we will get the solution for this problem u2. So now finally the solution, particular solution for the whole problem is given by u1 plus u2, which we already supposed in the initial stages, right? So this will give the particular solution to the problem. What is important in this is that we just need to check that if the boundary conditions are non-homogeneous, more than one conditions are non-homogeneous, then you can split the problem in this way, right? So hope you guys will understand this lesson. That's all for the time being. In the next lesson, we will start the Laplace equation in polar coordinates. So stay tuned and goodbye till then.